Okay, we've reached the challenge. It's about to become challenging. But what I want to do is let's use some of the math we already have up here on the board. Okay.
I think that'll save us some time and energy.
So when you add damping to a spring system, it changes the oscillation frequency. So this is no longer true.
Yeah.
So let's go ahead and fix that.
A very similar form, but we'll be adding some extra stuff.
Now, is it going to speed it up or slow it down, by the way?
Well, as the term kind of suggests, we're damping the
Yes.
motion.
Okay.
So I think we're subtracting something.
Okay, so I think we give you guys the formula and the activities. So the formula is similar but different to before. So we still have a K over M here, but we're subtracting this term. Now this B comes from the damping, right? Because there's an extra force, there's a constant times the velocity, and this B is the constant there. And so this is our new oscillation frequency in radians per second.
Mm-hmm.
And so what we really want to do is we want to connect this to the period, and then connect the period to the half cycle time. Now last time we learned that the period is t over 2. Okay, move so you guys can see that. And so that's pretty straightforward, but now we got to recalculate what the period is, because this is no longer accurate. Right.
So all of this stays the same, relating the frequency and the period to our angular velocity.
Mm-hmm.
But now when we substitute the expression for omega, we gotta update this. Polarize for me. So now I have this kind of nasty thing.
Yeah, Alex, it's a little bit messy now. All right. So that's what we get, and then the half cycle time. So now this is out of date. So let's erase this here. Hopefully I can fast forward this so it's not so uninteresting to watch. But so the half cycle time is half of the period there, and so that means that t half is just this divided by 2, and so t half. So that's going to cancel out with that 2 pi on the top, right? So it's just going to be pi over the square root of k over m minus b over 2m. Okay? And so what we can do is we can actually put this into a calculator and real quick just figure out what this is going to give for the case that we're trying to test it out. So, so do you remember what our k constant is?
That is 0.5.
All right, so k is 0.5. The mass here,
It's 13.
yeah, 13. So if the ship is collided with the blob, it's going to be 13. And then for the case that we're testing it out, we decided to use b of 2. Okay. And so I remember from the program. Do you remember what it was? I think it was 17.4. Does that sound familiar? Okay. So go ahead and write down. Find a place to write down measured 17.4. And what I'm going to do is I'm going to get out. I'm actually going to have to get out my laptop a little bit because this. All right. So survey says I just put this in my computer just now, and I got 17.4.
Ooh.
Haha. So our program's working, right? So not only does it work when the ship flies into the blob, not only does it work when the blob is oscillating without the ship, but it also gives the correct period when there's damping applied. Okay? So we've made sure to test our program in all the different situations that we could think of that we want to make sure that it works. So, all right. Well, nice job. Blythe, high five. Come back again sometime. Help us out, and hope you enjoyed this video.
Happy Thanksgiving.
Happy Thanksgiving. Right.